Good morning. We need to go over the 2019 uh, pre-response question number one. This is the one that involves drag and something being dropped into a fluid. Here's a copy of the picture that they give you. They start you with this object. They tell you the mass is 12 grams. That would be 0.012 kilograms. It's going to be dropped into a cylinder of fluid. And they give you a curve here. This is geez, I wish I could get this, there we go, into the picture. This is the velocity as a function of time, and it seems to be increasing like this. And they've drawn a best fit line on this thing already. For me, all the questions are on the back side, which is kind of inconvenient, but we'll get through it. The first question they ask is, does the speed of the object increase, decrease, or remain the same? And from this graph, it's pretty clear that the velocity is increasing. The line goes up and up and up and up. So this is going to be an increase. And they don't even ask us to explain or justify our response. That's pretty cool. Then in part II, they say in a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. Well, the direction of the acceleration is downward. You can get that from the very initial part of the motion where you let go at zero velocity and then it begins to move. And also, it just seems to be set up so that down is the positive direction. Now, what is the magnitude of the acceleration? And the magnitude of the acceleration is decreasing. Now, how did I know that? Well, the acceleration represented on this graph is the slope, and we start with a very large slope. The slope gets less and less and less, and then it's very nearly 1 here towards the end. Okay, so that's a very simple thing. You might want to add a couple more words of explanation on the day of the test. Using the graph, calculate an approximate value for the magnitude of the acceleration of the object at 0.2 seconds. And I have another graph here where I've done that in red. I used a ruler to draw a line that is tangent just above the curve, unfortunately, at the 0.20 of time. And then I found two places where it goes through grid lines, and I calculated the rise and the run and put them together to get this. I'll quote that as 2.2 meters per second squared for purposes of this particular problem. So let's go back to this here. So we would say calculated magnitude of, rise over run equals 2.2 meters per second squared at 0.2 seconds. Okay, and now we have a little extra piece of information right here. The students use this equation to model the speed of the falling object and find the best fit coefficients to be this and this. So they basically plugged in, I guess, this kind of an equation and asked a computer to find these parameters A and B so that it fit. A couple of words here. This particular model that is being used, this naturally is related to modeling the resistive force as B times V, which we did in class, and that's what led us to this this equation. When we did the differential equation, did the separation of variables and solved it, we had a natural log which we unnatural logged to get this kind of a form of the equation. So these two things go hand in hand. I don't know if it's a good move on the student's part to assume this. It certainly looks correct. It has that shape to it. Maybe it doesn't rise quite as fast as it should. So maybe there's not a really strong connection between those two things, but this is in the back of my head that we've seen this before, okay? Use the above equation to derive an expression for the magnitude of the vertical displacement of the falling object as a function of time. Okay, so we're going to have a function of time. Now, how do we get vertical displacement away out of a velocity equation? So we're starting with velocity as a function of time being a times 1 minus e to the minus bt, where a is 1.18 meters per second and b winds up being 5 inverse seconds. And the way that you get the vertical position is to integrate our velocity equation over time. And the limits are going to be 0 as a starting point and sometime t later. That makes this the first official use of the indefinite definite integral technique that I am so proud of. So we're going to integrate a 1 minus e to the minus b over t. The a is going to come out, and the integral of 1, oh, I forgot the dt. Calculus teachers would be upset. The integral of 1 gives us a t. Then we have minus, and then we have the integral of this thing. And when you do integrate e to the minus bt, the minus b comes down on the bottom of a fraction, and the minus sign cancels that, makes this a positive. So then we have 1 over b e to the minus bt, and that has to be evaluated at our two endpoints, t and 0. Putting t in for t gives you t plus 1 over b e to the minus bt. And putting 0 in for t destroys this term, but this term, putting a 0 in here, turns this into a 1. So we have a minus 1 over b. So I think the best thing to do would be to go ahead and collect up the things that all are multiplied by 1 over b, and then we have an e to the minus bt minus 1. I think I've got that right. I'm pretty sure. Let me double check. Yeah, that's looking pretty much right. They would give you credit for this. They would also give you credit if you put the numbers in these various places, which would be acceptable, but I'm not going to do it. That's part I believe, for this thing. And now we need part II. And part II wants us to find the force. And this is where we have a classic AP test wrinkle or little nugget of goodness, and that is that it's not easy to go straight from a velocity equation to force, but you can go from velocity to acceleration, and then once you do that, you just multiply that acceleration times the mass, and you'll get the answer. So they're going to have mass times dv dt, which is going to be mass times the time derivative of a 1 minus e to the minus bt. Okay, this is a pretty decent derivative to do. M times a, that comes out. We take the derivative of 1, it's nothing. We got a minus sign here. We take the derivative of e to the minus bt, and what comes out is a minus b. And let's see. Did they want a function? Yeah, they want a function. Okay, function of time, no problem. So we have to preserve this. We don't have any limits to put in. These two minus signs cancel, so let's collapse this all up and give them an answer. M, A, B, e to the minus b times t. And that would be the answer for part II. Alrighty, that brings us to C. And C is very interesting. In order to talk about C, I would like to remind you that when we solved this problem before, we got a velocity as a function of time, and it was mg over b times 1 minus e to the minus b over m times t. This was the result that we got last time. And we identified that this mg over b was something we had seen before. This was indeed the terminal velocity. So this means that if we try to make what they gave us match up with what we know, that would imply that A is exactly equal to the terminal velocity. So we can answer part C, I, very easily by just quoting that this is true. Another way to get at this is to take the form that they give you and take the limit as t goes to infinity. This term drops out, and you're left with just A. Now, trying to find the force that is exerted on this thing is a little trickier, and there is a true trick for it. Remember, our process is at first it's just gravity, then later our resistive force is reducing, and then finally when we reach terminal velocity, our resistive force is the same size as weight. And so this resistive force is hard to compute because we don't know exactly what lowercase b is. Obviously, lowercase b is somewhat related to uppercase b, but this is easy enough to do. this is just going to be equal to mg, which is equal to 0.012 times g. I'm going to use 10 for g, so 0.12 newtons. That's the simple and easy answer. The other answer would be to go back to our equation for the force. This is the force, the total force that is felt by the um, yeah, I guess that's not really that much different. I was going to say we could hmm. If you wanted to calculate directly, you would say that the force exerted by the fluid is B times V, and little b is somehow equal to capital B times m, and then this velocity is the terminal velocity, and that happens to be a. So we should get a force when we're at m times a times b. This should be the force, and it should be the same number, but it turns out it's not. When you put this in, and I think that a College Board may have made a mistake, or maybe this assumption that this is the form, this thing up here is the form of the solution is incorrect, because this does not work out, meaning they probably expected people to just make this identification that the force exerted by the fluid was equal to the weight, putting in B. You see, this would have to be equal to 10 or 9.8 for this solution to match that solution, and it's clearly not true. This is, maybe 6 on the outside. So I'm not certain that okay, here's what happened. In the grading, they talked about this being the answer, and they also said you would get full credit if you solve for it mathematically, and I think they meant doing this. So they did give credit for this. The fact that these two don't match up, I think, is a mistake made by the AP College Board people in their construction of this. I don't think they expected anyone to do this. They would have had to tweak these parameters a little bit, or it's an indication that this assumption and the resulting fitted parameters is not a perfect representation of what's really happening. Either way, I think the best answer to CII is just to realize that these two forces are equal and that the weight is a very easy one to calculate. All right, that's my solution for 2019 free response mechanics number 1, and we will be cracking into the next 2 this year, and I'll see you on the other side.